So to verify this thing is a solution to this differential equation, we want to take our y equal to c x to the fourth plus 2. And since we're going to try and verify that it's a solution to 4y minus 8y minus xy prime equal to 8, what we're going to do is we're just going to get all the pieces we need. We have y, we're going to jam that in there, right? This is going to go right there, and we need y prime. So to find y prime, we just differentiate. The derivative of x to the fourth is 4x cubed. The derivative of 2 is 0. So we're just going to substitute this in here, and then hopefully things work out. So plugging that in, I get 4 times cx to the fourth plus 2 minus x times c times 4x cubed. I'm not just going to write that it's equal to 8. I'm sorry, you can't see what I'm writing there. I'm not just going to write that it's equal to 8. I'm going to actually do the calculation and then see that it's equal to 8. I don't want to just write down the thing I'm trying to show is true without actually seeing it's true. So multiplying this out, I get 4cx to the fourth plus 8 minus 4cx cubed times x is x to the fourth. These cancel, and so that's equal to 8 as desired. So usually showing something's a solution to a differential equation is pretty straightforward. You're just finding whatever derivatives you need and substituting them into the equation, unless it looks like it's implicit, but that's usually not the case. Then the second part of this is to use the fact that y of 2 is equal to 50 to find the particular solution. I should scoot this camera down just a little bit because I keep wanting to go off camera. That's a little better. So all we're going to do is we're going to take our general solution, which is cx to the fourth plus 2, and substitute in 50 for y and 2 for x. So we're going to get 50 equal to c times 2 to the fourth plus 2. And then we're going to solve. So subtract 2, 48. 2 to the fourth is 16, so you get 16 times c, and then c is going to equal 48 divided by 16, which does simplify. 48 divided by 16 is 3. So c is equal to 3, and then you have to remember we're not done at this point, right? If you're trying to find the particular solution, you have to take that constant value and substitute it back into your general solution. So our particular solution is y equal to 3x to the fourth plus 2. Questions about that? Not too terrible usually. Then I'm going to close that door. So again, showing something's a solution to a differential equation, usually not too terrible. Finding a particular solution can be a bit of work depending on what kind of information you're given. Let's continue on though and talk about separation of variables, because that's, so typically when we talk about solving differential equations as opposed to just checking to see if something's a solution, there's really only, well, I should say, there's only 2 methods we're going to learn about in this class. There's separate, well, I should say there's at least 1 method, maybe 2 methods we're going to learn about. The one method we're going to learn for sure is separation of variables, which we'll talk about today. And there is another method which most of the time does get covered. It's called first order linear differential equations, and it involves using what's called an integrating factor. We will talk about that if needed. It's usually covered, but sometimes people skip it. So I don't want to cover it if you don't need to see it, but we'll probably end up seeing it. So some paper here. Cool. So let's kind of work through an example while we talk about the steps. So our example is going to be to solve the following differential equation. What do I got here? I've got dy dx equal to 6x squared y plus 12x squared. And then on the right-hand side here, we'll write down the steps. Steps for solving a separable differential equation. You should definitely get used to people abbreviating differential equation with diff-EQ. It's pretty standard. So when you're solving a separable differential, well, first of all, you don't know it's separable to start off with. Usually, well, no. So assuming it's separable, here's what I'm going to do. I'm going to get rid of this dx on the bottom. I don't want any dy or dx or dt or whatever your independent variable is, d thing in the bottom. So I'm going to multiply both sides by dx. So that's your first thing. Multiply both sides by d whatever. The d thing that's in the bottom. So then you're going to get dy equal to all this stuff, 6x squared y plus 12x squared times dx. And what that kind of does to help us not make any mistakes is it kind of traps all this stuff together, right? You can't bring any of this to the other side via subtraction or addition, right? Because if you did, you'd also have to carry the dx with you. You'd have to multiply the dx through, which you don't want to do. So you want to separate variables, and it's called the thing it's called for a reason, because you want y's and x's completely divorced from each other. And since the dx is on the right and the dy is on the left, we need all the other y's to come to the left. Before you can do that, you typically have to factor the right-hand side in some way if it's not already. So usually the second step is to, what is that right here? I said, oh yeah. So write that stuff, write the stuff as y things times x things. This is the step where things might fall apart. It might not be possible to do this if it's not separable. So here I see that from 6x squared y plus 12x squared, I can factor out a 6x squared. Or really importantly, an x squared. But I'm going to do the whole 6x squared. So I'm going to have dy equal to 6x squared times, I've got a y plus 2 times dx. And then the third step is we want all the y things on the left, all the x's on the right. Again, I should really say we want all the y's on one side, all the x's on the other side. I typically do it in this way, so the y's are on the left and the x's on the right. But if you do it another way, you know what you're doing. And I should point out at this stage, the only way we can do that is by using multiplication and division. We cannot add or subtract pieces. So I'm going to divide both sides by y plus 2. So I'm going to have 1 over y plus 2 equal to 6x squared dx. Oh, sorry, 1 over y plus 2 dy. So those are the steps for getting it to a place where it's separated, and the rest is integrate and solve, which is, I know, kind of a lot to say in one step, but we're going to integrate both sides and solve for y. So let's see here. So anti-differentiating both sides, the antiderivative of 1 over y plus 2 dy is equal to the antiderivative of 6x squared dx. So this is where all of your anti-differentiating skills from 16b are going to come into play, right? You're going to see not all the usual things, but you'll probably see some u substitution. You'll probably see some natural logarithms. You'll probably see some integration by parts, right? All those things are going to come back. So just be aware of them. So integrating 1 over y plus 2, that's going to be the natural log of the absolute value of y plus 2. And integrating 6x squared, I'm going to get 6x cubed over 3, which is going to be 2x. 6x, I said 6x cubed, yeah, over 3, so 2x cubed plus c. You always want to put the plus c, I mean, technically, right, there's a plus c on both sides. We bring them over to one side. You always want to put the plus c on the side that doesn't have y, because you're trying to solve for y, so you want to isolate the y variable. Couple things. Most of the time, we should actually be able to solve for y, like isolate it completely. Occasionally, you won't be able to. Maybe you have like a bunch of y's over here and you just can't do it. That's fine. You just leave it as is. But if you can solve for y, typically you're expected to. I want to address this absolute value here because it's kind of a pain, but it's not really a pain. So long story short, you can almost always just ignore that absolute value. You can just write it as a parentheses and it's going to go away. Here, but let me show you why that happens, because I think it is worth seeing at least once so you can really believe that it's okay to do the thing that you're doing. So not really enough room. I could maybe make this fit. Sure, let's try and make it fit. So first we're going to e both sides, right? We're going to do e to the natural log of y, absolute value of y plus 2 equals e to the 2x cubed plus c, which I'll point out is equal to e to the 2x cubed times e to the c. Right, when you add in the exponent, it's just that times that. So then what we're going to say is, great, e to the natural log of some stuff is just the stuff. That's why we did it. So I'm going to have the absolute value of y plus 2 equal to, I'm going to write this e to the c in front just because it's more typical to do so, e to the c times e to the 2x cubed. And now here's where we kind of get rid of the absolute value. So if the absolute value of y plus 2 is equal to this thing over here, I want to point out, no matter what c is and no matter what x is, e to anything is always positive. Think about the e to the x graph. Right? The e to the x graph is always above the x-axis, so it's always got a positive y value. So this is always positive here. But the insides of this could be positive or negative. Right? Y plus 2 could be positive and the absolute value would be positive. Y plus 2 could be negative and the absolute value would be positive. So what we're going to say is that y plus 2 on its own could be positive or negative e to the c times e to the 2x cubed. And now here's what we're going to say. This plus or minus e to the c is some constant. It's either positive or negative. And if we're given an initial condition, we can figure out what it is exactly. But for now, we're just going to call it a constant. I typically like to call it A. Some people just like to call it C again, whatever you want to do. But we're going to write this as y plus 2 equal to, I'm going to call it A e to the 2x cubed. And then finally solving for y is going to equal A e to the 2x cubed minus 2. So usually when you're doing this process, one, if you're eing both sides, you're always going to be having that constant turning into like a multiple of your function as opposed to something you're adding on at the end. But more importantly, you can kind of just ignore the absolute value if you have absolute value there. It's almost always just going to disappear in a convenient way. Sometimes this constant will be positive, sometimes this constant will be negative, but it completely depends on what your initial condition is. Okay, so that's kind of it as far as, I mean, that's the general process for solving a separable differential equation. Let me see. Let me point out a couple of examples that wouldn't work. So here's a really easy example of something that's not separable. Let me make sure I keep my notes in order here. It's always a challenge. So here are some not separable differential equations. What have I got here? dy dx equals x plus y. Looks pretty simple, definitely not separable. Right? You can't write so basically to be able to have it be separable, you have to be able to write the derivative equal to a function of x times a function of y. And there's no way to write this as stuff with x's times stuff with y's. I really should say stuff with just x's times stuff with just y's, right? You could factor out an x here, but it would be x times 1 plus y over x. That second piece would still have, right? Here's your x times 1 plus y over x. That's definitely a function of x, but this part here is not a function of y. So it's not separable. There's no way to get the x's and the y's separate from each other. I should point out, we'll see this later on. We'll come back to this one maybe on Friday, and we will have class on Friday. I will be here on Friday. This one we can be solved using first order linear differential equations, which I'm going to abbreviate as FOLD. Is a first order linear differential equation. First order differential equation just means the highest derivative you have is the first derivative. A second order differential equation, the highest derivative you have would be a second derivative, and so on and so on. And the linear part refers to the fact that it is linear in your variable y. So right, you don't have like y squared or y cubed or some other weird stuff. You just have y to the first. Those types of differential equations have a very specific method of solving them that we will probably talk about. Here's another example of something that's not separable. Dy dx equal to y over x squared plus y. There's just no way to get the x's and the y's separate from each other. Can't do it. Like you could try, right? Let's see. I could say I would probably try this first: x squared plus y times dy equal to y times dx. And that seems problematic. I could divide both sides by y. X squared plus y divided by y, dy equals dx. I've got x squared over y plus y over y. And it doesn't look good, right? Because it's not going to work. Because again, I can't get this over here by just adding or subtracting. I can't, there's no way to make that happen. So yeah, usually if you're asked to use separation of variables though, it will be separable. No one's going to try and make you do a thing that's impossible typically, but someone could ask you, and I've definitely seen on exams and homework assignments, is the following differential equation separable? Yes or no? And so sometimes they'll try to trick you and make it look like it might not be separable, but really you just have to do some factoring. For example, I can think something here real quick. Is the following, sure, dy dx equal to x squared y squared plus 2x y squared plus y squared. That's a little too easy, James. Fine. Fine. Is this separable? Exactly. Yeah. So typically, even though I said I like to multiply by dx first, because it kind of doing that makes sure that I'm getting my dx's on the right side and my dy's on the left side. Really, what I'm often looking for first is, can I write the other side as something with y's times something with x's in it? And yeah, we totally can here. We can write this as dy dx equal to y squared times x squared plus 2x plus 1, which you can even write as y squared times x plus 1 squared. So then we could rewrite this as dy over y squared equal to x plus 1 squared times dx. And let's go ahead and solve this one. It's not bad to solve. So let's go ahead and solve. Practice stuff like this. So let's solve the differential equation dy dx. I'm going to write it simplified. Dy dx equal to y squared times x plus 1 squared. So we do separate, even though I know we already separated them. We're going to do it again. You can either write dy over y squared. I find it more helpful to write the dy off to the side. So I would rather write it as 1 over y squared times dy equal to x plus 1 squared times dx. That's how I would prefer to write it. But if you like dy over y squared, that's also totally fine. And we're going to integrate both sides. So a couple things. On the left-hand side, I would rewrite that as the integral of y to the -2. And on the right-hand side, we could do a u substitution, but I don't really think we need to do it. Like, right, we can be like, well, you know, we're thinking u substitution here, but really if u equals x plus 1, then du is equal to dx. And so this really just becomes u squared. And the integral of u squared is u cubed over 3. So we're thinking this is going to be a u cubed over 3, which is really just going to be an x plus 1 cubed over 3. What I'm trying to say, maybe in a roundabout way here, is that if you've got something that's just like x plus something or x minus something to a power, you can kind of just use the reverse power rule, like x plus 1 is your variable. So we can do this as x plus 1 cubed over 3 plus c. And now we're going to anti-differentiate the left-hand side. So we're going to get, let's see, y to the -1 over -1 equal to x plus 1 cubed over 3. Okay, so some things to think about. Let's see, how do I want to say this right away? Yeah, so we're going to solve for y, and we're also going to, we'll introduce an initial condition in a second. So solving for y, I'm going to multiply everything by -1. So I've got y to the -1 equal to negative x plus 1 cubed over 3. And here's what's going to happen most of the time when you see someone solve this stuff. Anytime you add to a constant, you add a constant to a constant or multiply a constant by a constant, we're just going to call it the same constant. So a constant times -1, still a constant. Even though, right, it may be, right, it's actually changing. And some people like to do this thing where they call this C1, this C2. Every time you change it, you call it a new C. But most people don't do that. But if you do anything else, like take the sine of both sides or the square root of both sides or invert both sides, then you can't just say it's the same thing. You have to actually do that too. So when I see y to the -1 equal to this, I've really got 1 over y equal to all of this stuff here. Negative x plus 1 cubed divided by 3 plus c. And if I want to solve for y, I need to take the reciprocal of both sides entirely. Now, if you don't like that because it feels kind of hand wavy, you could do the other thing where you just multiply both sides by y. So if I multiply both sides by y, I'm going to get y times this equal to y times this. So then we have 1 equal to all that stuff, negative x plus 1 cubed over 3 plus c times y. And then to isolate y, we're just going to divide everything by this stuff that's multiplying by y. So we're going to get 1 over all of that, negative x plus 1 cubed over 3 plus c. I don't really need parentheses there, but I wrote them anyway. And if I were simplifying this to make it look nicer, I don't usually like fractions and fractions. So I would multiply the top and the bottom by 3 to get that y was equal to 3 over 3 times this is going to just be the negative x plus 1 cubed. And 3 times a constant is still a constant. So this would be my general, or one way of, right? You could totally write it like this, but this would be like the preferred nicer way of writing my general solution. Now, what if we were given some initial conditions? Let's say our initial conditions were y equal to, I'm going to try and make something, I'm just going to make something up and we'll hope it turns out okay. Y equal to 7, that's going to be awful, I can tell already, when x equals 0. So try and not make it too terrible. Okay, so we want to find the particular solution. All we're going to do is just plug those things in. Now, I should mention, sometimes you will see a better place during this process to actually find your C value. Usually it's at the end, but sometimes, what problem is it? There's a particular type of problem specifically where it's like, it's easier like halfway through to just plug in for C, but usually we just plug in at the end. So if I plug in my initial conditions here, let's see, I'm going to get y is 7, and I'm going to have equal to 3 divided by x is 0. So I'm just going to get negative 1 plus c. Okay, that's not too terrible to solve for. Sure, I would probably multiply both sides by the denominator here. So I'm going to get 7 times negative 1 plus c equal to 3. Negative 7 plus 7c equal to 3. 7c equal to 3 plus 7 is 10. C is equal to 10 sevenths. So our particular solution under those initial conditions is going to be y equal to 3 over negative x plus 1 cubed plus 10 sevenths. And if you really wanted to, you could multiply the top and bottom by 7 again to have something that looked nicer. The reason I point this out is not because I really recommend doing it, but if you're looking at answers in textbooks, they will often do this step without showing the step. So you might think this is your nice answer, but your textbook might say, well, I'm going to multiply the top and bottom by 7 and say it's y equal to 21 over 10 minus 7 times x plus 1 cubed. They might write it that way instead. So just be aware of that if you're trying to actually see an answer and it looks different than what you were kind of expecting. Questions so far? Okay, let's see. I forgot any other cool examples here. Yeah. We should talk about this one. Okay. Sure. Let's go back a step just to kind of look at an easier example for a second. Actually, let me grab that example. So I've got lots of examples. I'm kind of just thinking about. Let's do this. Let's solve. I don't know. Try to reuse pieces of paper, but it just doesn't look good. See through it. You can have another life somewhere else. Okay. So let's try solving the following. What have I got here? Where'd you go? Yeah, dy dx times cosecant of x is equal to 5 minus y. So some of the time, you won't always just have dy dx equal to some stuff. You'll have dy dx multiplied by other things equal to some stuff. The process is still the same. If you're trying to solve it, you really only have two choices. Right, so if someone says solve, the first thing you should think of is, can I separate it? The answer will often be yes, but if you can't, then the answer is going to be the other thing we haven't learned yet. And that's really it. Like if you're solving a differential equation in 16Z, those are your two options. Is it separable? Yes, great. No, do the other thing. So here we're going to separate. We're going to bring all the y's to the left, all the x's to the right. So I'm going to say that dy is equal to 5 minus y times dx divided by cosecant of x. So multiply by dx and divided by cosecant of x. And then I'm going to divide both sides by 5 minus y. So I'm going to have 1 over 5 minus y dy. I'm also going to be smart about this. I don't know how to integrate 1 over cosecant, but I definitely, well, I mean, I do if I rewrite it as what it's equal to, which is sine. So 1 over cosecant of x is just sine of x. And that's going to be much less terrible to deal with. And then we integrate. So integral of 1 over 5 minus y dy equals the integral of sine of x dx. Okay. So integrating 1 over 5 minus y, it's almost the natural log of the absolute value of 5 minus y. What am I missing though? Yeah, it's negative. And then the antiderivative of sine of x is negative cosine of x plus c. Now, if I were solving this, well, no. If we're trying to solve for y, regardless of what's happening over here on the right-hand side, we want to get rid of that negative sign first. So, which works out nicely here, right? We can immediately say, oh, I've got natural log of the absolute value of 5 minus y equal to positive cosine of x plus. I'm going to do this. I'm going to do the subscript thing this time just to kind of show you just to show it, but it's not really necessary. E both sides, e to the natural log of the absolute value of 5 minus y is equal to e to the cosine of x plus c2. Get rid of or rewrite the left-hand side as just the absolute value of 5 minus y. That's going to equal e to the cosine of x times e to the c2, which you could, no, I don't want to call it that yet. I really do find it useful if I'm showing my absolute value stuff, not that I think you need, right? So at this point, really, you should just do the following. Here's what you should do, and then we'll show the work behind it again. So the next step would be to say, okay, 5 minus y equals, let's call this c3. c3 times e to the cosine of x. But really the work that we're skipping is we're saying, oh, really 5 minus y equals plus or minus e to the c2 times e to the cosine of x. And then we're calling this plus or minus e to the c2. That's our new constant c3. That's what we're really doing there. But I think you probably never have to show that step because it always works. And then finally solving for y, I would probably just add y to the other side. So would I? I don't know. Negative y equals c3 e to the cosine of x minus 5, and then multiply both sides by -1. Y equals -1 times a constant is a new constant, c4 e to the cosine of x. Cool. So my general solution, right up here, is y equal to c e to the cosine of x plus 5. And you can check it if you really wanted to. I don't think we need to, but if you took the derivative of this and multiplied it by cosecant and then did 5 minus that, you would get the same thing. Yeah, that works. In fact, we can kind of even see it. If you took the derivative of this, you would get e to the cosine of x times negative sine. If you multiply that by cosecant, the sine and the cosecant would cancel, and you'd have negative your thing, and then the other side would be also negative your thing. Yeah. Okay. Let me ask you all. Find the particular solution for the initial condition y of pi over 2 is equal to, let me think for a second here. Is equal to 2. Yeah. Yeah, let's see. What'd you get for your constant value? Is it negative? Let's see. That seems right. Let's check. So if I plug in pi over 2 for x and 2 for y into my general solution, I'm going to get 2 equal to c e to the cosine of pi over 2 plus 5. Okay, we have to remember what cosine of pi over 2 is, which is 0. So that's going to be e to the 0, which is 1. So we really got 2 equal to c plus 5, which means c is equal to -3. I'm going to say it every time. We can't stop there. We don't have to write the particular solution. So the particular solution is plugging that back into your general solution. So it's going to be y equal to -3 e to the cosine of x. Cool. So separable equations, separable differential equations aren't really that terrible to do. You just have to make sure you can get the y's on one side and x on one side. And really then it's just kind of rely on your anti-differentiation skills. So once you've separated, you are then going to be at a place where you're having to anti-differentiate things. And it might be easy, it might not be easy, depending on what you've got. Let's look at, let's look at it. Yeah, we'll do this one. I was going to do this other one, but let's do this one first. Cool. Let's look at the following problem, which we're going to talk about in a couple of different ways. Let's say we're going to solve y prime minus 3x squared y equal to x squared. Now, I said something before that might not be entirely true. It's true, but just not the way I was saying it. When you're solving something and you think it's separable, you can't really add or subtract both sides. You're really only allowed to do multiplication and division. But I should say that's true once you've gotten to the place where you have dy dx equal to all the other stuff. If you have dy dx plus or minus some other stuff, you want to add or subtract to get all that stuff on the other side. So our first step here should be to rewrite this as dy dx equal to 3x squared y plus x squared. And then we're going to hopefully separate the right-hand side. And we can. We can definitely write the right-hand side as a function of x. Let's say x squared times a function of y. 3y plus 1. Great. And now the process is very similar, right? We've done this a few times. I feel like I wanted this to be slightly different now than looking at it. Let me check one thing. No, I definitely didn't. I'm just a liar to myself. Okay, that's fine. So we're going to do the usual thing. Let's see here. I'm going to bring the y's to the left. So I'm going to have 1 over 3y plus 1 times dy equal to x squared times dx. And we're going to integrate both sides. All right, I want you both to do the integration of both sides on your own. The right-hand side shouldn't be too terrible. The left-hand side, there is a little extra piece you need to be careful about. You don't have to solve it after that. I just want you to integrate both sides. Oh. I mean, you can do work ahead, but like I wanted to get to the same place. So when we integrate that left-hand side, we do get a natural log of the absolute value of 3y plus 1. And so, or if you don't mind me asking you, what else do we need over here? It's okay if you don't know. Sure. So let me ask you a different question. If I took the derivative of the natural log of this stuff, what would I get? Like, what's the derivative of the natural log of x? One over, right. So I take the derivative of the natural log of some stuff, I get what? Yeah, but then because of the chain rule, what would I have to multiply by? By the, not the stuff, but the what of the stuff. Not the natural log of stuff, it's actually the derivative of the stuff. Remember the chain rule? So if I take the derivative of this, I get 1 over 3y plus 1, but then I have to multiply by the derivative of 3y plus 1, which is 3. But I don't have a 3 here. So to account for that, I need a 1/3 out in front. So that's typically what happens when you have like the integral of 1 over 3y plus 1 is you end up dividing by that. Or more, if you had something else like, for example, the integral of 1 over 5 minus 2y dy, you would get exactly the natural log of the absolute value of that stuff then you have to divide by a -2 because the chain rule would make you multiply by a -2. So then after that, it's not terrible. I mean, so it's a matter of opinion, I guess. To me, this feels like the work, and the rest of it's just like, okay, we have to do the algebra to get y by itself. It's not terrible, but it's also not fun. So solving for y, I'm going to multiply both sides by 3. So I'm going to get the natural log of the absolute value of 3y plus 1 equal to 3 times this is going to be x cubed plus a new constant, which I'm going to call the same constant. We're going to e both sides, and we're just going to ignore the absolute values because we can. So we're going to say that 3y plus 1 is equal to e to the x cubed plus c, which turns into e to the x cubed times e to the c, which then we're going to rewrite as 3y plus 1 equal to a new constant times e to the x cubed. And we're thinking of that new constant as e to some other constant. Finally, we solve for y. 3y equals a constant times e to the x cubed minus 1. And then finally, y is equal to, if we divide everything by 3, a constant divided by 3 is still a constant. And 1 divided by 3 is 1/3. Cool. Yes, right on. So there's your general solution. I'm not particularly interested in the particular solution. Made myself laugh with my plan. Okay, but here's what I actually wanted to show you was that although we solved this one in what I would consider the usual way of doing it, this particular differential equation is also a first order linear differential equation. Let me show you what I mean. Question.
Why is the c e to the x cubed not divided by 3?
Well, it is because this is right, right. So going back, here's my C1, here's C2 because I multiplied C. So C1 or C2 is C1 times 3. And then this right here is e to the C2, e to the C2, e to the C2 is my C3. And then dividing both sides by 3, C4 is my C3 divided by 3. Right, so it's still just another constant. Right, you can totally think about the function being divided by 3, but you can also think about just the constant being divided by 3. So it's totally fine to say that this part here, this C4, is equal to C3 divided by 3. So whenever you're adding a constant, subtracting a constant, multiplying or dividing so if we're adding a constant to a constant, or subtracting a constant from a constant, or multiplying a constant by a constant, or dividing a constant by a constant, you can just call it another constant. You don't have to like say it's the constant divided by 3. Oh, constant divided by 3, new constant. But then we're lazy mathematicians, we just call them all C because we do. Okay, so I'm going to show you this, even though there's a small chance you might not see it in class. I really doubt it though. You almost likely for sure will see first order linear differential equations. So we could solve this in another way. And not that you would, like usually we reserve this method only when we have to use it, but it's good to see that using it still results in the same answer. So we're going to solve this a different way. And this is, I might encourage you, we might not have enough time to do it because it's 10:48 and I don't want to keep you too late. So here's what I'll say. Next time, we will solve that differential equation, y prime minus 3x squared y equal to x squared, using first order linear differential equations, which requires an integrating factor. Here's what I will tell you. To be first order linear, I don't love writing out, but I should write it down at least once. To be a first order linear differential equation, we have to be able to write it. We have to be able to write the equation in the following way: as y prime plus some function of x times y equal to some other function of x. So I will point out that this derivative here, this first derivative, is giving us the first order part of our name of this type of equation. And this y to the first power, that's what's giving us the y to the first, not the derivative of y, right? Just y to the first, which is equal to y. That's giving us the fact that it is linear in the variable y. Just like y equals 3x plus 2 is a linear equation because x is to the first power. Same idea here. This is a linear differential equation in y because y is only raised to the first power. There isn't a y squared or a square root of y or a y cubed or any other funky thing like that. You can only have y to the first. So if and only if you can write your differential equation in this particular way, you can use the process that we'll talk about on Friday. I will point out that this equation certainly qualifies because you can write this as y prime plus, and it is important to recognize that we need a plus there, negative 3x squared times y equal to x squared. So in this example, the function of x here, p of x, which is standard way to call it, is negative 3x squared. And you definitely need to be aware of that negative sign. And q of x is x squared. And on Friday, we'll talk about how we can use the other method of using an integrating factor to solve it. It's kind of neat. It's neat that this particular type of equation, no matter how wacky the function here and the function here are, can always be solved in a very particular way. Or I should say a very general way. I wouldn't say that. I would say sometimes it doesn't get covered in 16C, but usually it does. No, it's certainly just as common. The thing about differential equations is that there's a whole boatload of ways of solving them. Like there's a whole class, Math 22B, that's devoted just to solving differential equations. You learn like all sorts of techniques. I am not particularly good at it, but I am good at these two methods, which is good because they're the only ones we learn in this class. But yeah, there's lots of other ways of solving differential equations. It's a whole field of mathematics devoted to solving differential equations. But it's 10:52. I should let you go. We'll definitely talk about this next time.